Good afternoon, everybody, and thanks for being here, listening to my presentation about wearable and flexible pedobarographic insole for continuous pressure monitoring under the sole. So, this is the outline of my presentation, and after a brief introduction to piezoresistive materials, I will tell you about piezoresistive rubbers based on tunneling effect. I will show you a couple of previous works we have done in Italian Institute of Technology, and after an introduction to synthesis and methods of realization of the sensor, I will show you the piezoresistive characterization and the realize of the real sensor and system. So, starting from the background we have about tactile sensor technologies, we wanted to realize a multi-layered sensing structure for continuous pressure monitoring under the insole, which is very important in, for example, biomedical fields for monitoring the behavior of patients with different injuries or pathologies. Now, we want to realize a sensing material with high performance in order to be competitive with already available on market systems, which are actually quite expensive. And we want the material have good flexibility and mechanical stability, and we want to realize a system that presents very low energy consumption and very large work conditioning range. So, the piezoresistive polymeric composites mainly can be divided into two great categories, which are pressure conductive rubbers that use a smooth conductive particle inside the polymeric matrix, and the connectivity is the type of 0, 3, or 1, 3, where the first number is about the connectivity between the particles, and that means that 0 means that the particles are completely not in contact between them, and 1 is that they are in very small contact. Electrical resistance varies with the pressure in about 6 orders of magnitude, and the conduction mechanism between the particles is the percolation model. The other great type of piezoresistive rubbers is quantum tunneling hybrid-based materials. And the filler are conductive spiky particles, and the fundamental part is that are the spikes, because thanks to the spikes the electric field increases, and it is possible to apply the conduction mechanism of the Fowler-Nordheim tunneling model. So, previous works we have done a work using nickel as a metal filler. And you can see here the magnification with the pheasant, and you can see that particles are finally dispersed into the polymeric matrix. These are the results we obtained, and as you can see, varying the percentage of filler into the matrix, we obtain a different response to the pressure. The numbers up here means that for one part of resin, there are 2.5 up to 5.5 parts of filler. Another previous work regards gold particles, which are homemade by deep protective solvent solution, and even in this case, the particles are dispersed into polydimethyl siloxane matrix. And even in this case, the dependence between pressure and resistance is a logarithmic one. So why do we choose copper? It is because it has no safety problems with respect to nickel. It is, of course, more cost effective than gold. It is less material needed for the same performance in sensitivity, and it has a higher conductivity with respect to nickel and with respect to gold. So we used a commercial available metal filler. As you can see, the particles are quite spiky, and they have an average size of 20 microns. and we used as a matrix, a polymeric matrix of 2-part silicon. And by controlling processing variables like dispersion and transit parameters, filler mount, and so on, we are able to finely tune the sensitivity of the material. So these are phase and magnification of the composite material, and even in this case, the particles are finely dispersed into the matrix. And as you can see in the bottom, our material is quite flexible and mechanically stable. The piezoresistive characterization was made using a universal mechanical testing machine connected with a source meter in order to measure the current related to a precise pressure applied. And as you can see, we have done the characterization varying the amount of filler, and the best results are obtained for 250 PHR, that means per 100 resin. So 250 parts of filler per 100 parts of resin. So decided we will use the 250 PHR composite. We tried to vary the thickness of the sample, and we decided that the best one is 1 millimeter thick, because the resistant values are well spread among 7 orders of magnitude, and especially they are quite good for our operating range. The preparation of the sample was made by weighting the components first and then mixing them in an automatic mortar. And after the casting molding, we cooked it into a vacuum oven at 70 Celsius degrees for 4 hours. The material was then sandwiched between two Kapton metallized layers, and which is then photolithographically processed in order to obtain the electric connections. And then the sensor is connected to the electronic part. The electronic part is composed by 8 by 8 matrix array, and the measurement performed is the measure of the current for each node. We use a logarithmic trunk impedance amplifier that presents a very low leakage current in order to not to cover the little current measured in case of very small loads. The sampling rate of the whole matrix is 16 Hertz, since every node is sampled at 1 kilohertz, and we have 64 nodes. These are the results for the first functional test. As you can see, the picture are coherent with the load conditions. So when the feet is completely in contact with the ground, we have a uniform distribution of pressure. The results are obtained interpolating by software the measurement of the current in order to obtain smooth pictures and quite easy to read. So in summary, we obtained a process optimized for this copper PDMS composite. We obtained a huge piezoresistive variation up to 8 orders of magnitude. We obtained a tunable pressure sensitivity, and we developed specific electronics for this sensor, and we did a proof of concept of a flexible piezoresistive pedobarographic insole. Future work will involve the pressure, the sensor electronic integration, and it will be nice if it will be integrated with wireless communication to the computer. And finally, we will do functional tests in order to evaluate long-term activity of the sensor. That's it. Thank you.